Let us discuss the method which is called as decimation in time or DIT method for computation of DFT. Now, there will be two methods by the name as DIT/FFT for calculation of DFT. Similarly, DIT/FFT could also be used for IDFT calculation. So, whenever the question is asked in the examination, please read the data properly and conclude as to it is a DFT calculation or a IDFT calculation. So the present discussion here is about decimation in time FFT, which is used for DFT calculation. Now, DIT/FFT method, the end point is divided into two parts. One consisting of even numbered samples and other consisting of odd numbered samples. The algorithm assumes that we are using n, which is always a power of 2, or it is radix 2 method. We are aware that the DFT of a sequence x of n is given by the expression x of k is equal to summation n lies between 0 to n minus 1 x of n into wn to the power of kn. We number this equation as 1. Now separating this x of n into its even and odd numbered points. So in x of n, selectively we have to take those values which have even index. For example, we have 2, 4, 6, etc. They are even numbers, and we have odd numbers 1, 2, 3. The very first even index is going to be 0, and the last even index is going to be n minus 2. Because n value we have chosen to be radix 2, the value of n will always be even. Therefore, n minus 1 will be an odd number. The previous even number is n minus 2. So the meaning of the summation is that we are taking limits between 0 to n minus 2, but we are taking only selective index which are even. Similarly, the first odd index is 1 and the last odd index is n minus 1. Selectively, we are taking those indices which are only odd. Now, let us change the form of this particular equation. To represent even numbers, we substitute n is equal to 2r, and to represent odd numbers, we substitute n is equal to 2r plus 1. Therefore, making these changes in the equation 2 requires us to recalculate the limits because we are substituting for the value of n. N is going to be replaced with some quantity, that is r. Therefore, we can compute the limits as shown here. For n is equal to 2r, the limits originally was n is equal to 0 to n is equal to n minus 2. If we solve for r using the above equation, the r value becomes equals to 0 and the r value becomes equals to n minus 2 divided by 2 for the value that is n is equal to n minus 2. Simplifying, we get the upper limit as n by 2 minus 1. Similarly, for odd, n is equal to 2r plus 1. The previous limit was n is equal to 1. When you substitute n is equal to 1 and solve for r, we get the value of r as 0. Similarly, substituting n is equal to the upper limit n minus 1 yields the new limit r is equal to n by 2 minus 1. So it is notable that in both cases, the lower limit starts from 0 and the upper limit becomes n by 2 minus 1. Now, incorporating all these things in equation 2, the equation 2 becomes, so the limit is now in terms of r, it is between 0 to n by 2 minus 1 in both the summations. We have changed n to 2r here and 2r here. We have changed n to 2r plus 1 and 2r plus 1. The substitutions are complete. Now let us look whether we can simplify any term here. If you look at the last term in the second summation, the trivial factor power, it can actually be split into two terms. The two terms are wn to the power of 2rk into wn to the power of k. Now let us consider that Wn to the power of 2 Rk, which is common in both these summations. Now Wn to the power of 2 Rk expressed in the exponential form, and we see that the 2 which is the power can brought inside and it becomes n by 2. Therefore, Wn to the power of 2 Rk could be expressed as Wn by 2 to the power of Rk. Next, let us make these changes in the previous equation, and we can see that the real factor is now Wn by 2 to the power of Rk, Wn by 2 to the power of Rk, and of course the factor which is Wn to the power of k, which is independent of R, can be treated as a constant and can be taken outside the summation. So Wn to the power of k is written outside the second summation. Now, in the above equation, we have two summations. Each of the summations can be given a name. The name given for the first summation is called as g of k. The name given for the second summation is called as h of k. Now, g of k represents an n by 2 point DFT. H of k also represents a n by 2 point DFT. This fact is confirmed by inspecting the limits. The limits are from 0 to n by 2 minus 1. This is n by 2 point sequence. Also, the twiddle factor, you can see that the value of n here is now n by 2. So in total, we can consider each term here to represent an n by 2 point DFT. Now equation 4 is an important tool for us to describe an n point DFT x of k, taking the help of smaller DFTs of size n by 2 each. Now we can create a structure which is provided by equation 4. The manner of obtaining the structure is very simple. We just have to substitute different values of k. Let us assume for simplicity that n value is 8. For 8 points, let us build the structure. Now for 8 points, the first k value we will start with is 0. And the last value of k is going to be 7. So between 0 to 7, we have to calculate all the outputs. Now, as you can see, the value g of 0 plus wn to the power of 0 into h of 0 is the result x of 0. Similarly, x of 1 can be computed by substituting the value of k as 1, and we get appropriate powers for the twiddle factor also. Now, using this condition, we can make the arrangement as shown here. The arrangement shows that we have grouped the input into two categories. One is even numbered points, one is odd numbered points. Even number is fed to a block which is an n by 2 point DFT. The result of this is called as g of k. So g of k represents an n by 2 point DFT. The inputs are even numbered inputs. Similarly, h of k represents the DFT of the set of inputs which were odd. So we got the result G0, G1, G2 up to G3, and we got the answer H0, H1, H2 up to H3. Now equation 4 teaches us how to combine this G of k and H of k to get the output called as X of k. We have already inspected the value that X of 0 is the sum of G of 0 and H of 0. Therefore, to get G of 0, we are just taking the data from the first signal line. And H of 0 is tapped from this particular point, and we are adding it at this particular node, and the sum is called as X of 0. Please note, H of 0 is scaled by Wn to the power of 0. Similarly, G of 1 added with the scaled version of H of 1. The scaling is Wn to the power of 1. Gives you the result x of 1. In similar lines, we can say x of 2, x of 3 is calculated. Coming to x of 4, we are going to exploit the periodicity of the DFT. We have outputs which is G0, G1, G2 and G3. G3 is the last number. So when you substitute the value of 4 here in the equation, it becomes G of 4 and H of 4. G of 4 is nothing but G of 0 and H of 4 is nothing but H of 0. Therefore, once again we can combine G of 0 with h of 0 scaled by w into the power of 4, result is x of 4. And similarly, the rest of the values are also expressed. So this is called as the first decimation, wherein we have expressed the n point DFT taking the help of two n by 2 point DFTs. Here are the substitutions wherein we have considered the value of k from 0 to 7. This is just to support the argument. We have shown the various substitutions and what combinations are required to generate the answers for x of 0, x of 1, x of 2, x of 3, x of 4, then x of 5, 6 and 7. So the same thing has already been discussed about. The inspection of these equations will tell you how we obtain the structure. Next, let us consider the single equation called as g of k. Now g of k equation we have seen is summation r from 0 to n by 2 minus 1 x of 2r wn by 2 to the power of rk. This was the n by 2 point DFT of the even numbered points. Now let us separate this x of 2r once again into even and odd numbered points. Therefore, we get r from 0 to n by 2 minus 2 represents even, and r from 1 to n by 2 minus 1 representing the odd numbered points. And here again we are putting r is equal to 2l for even, r is equal to 2l plus 1 for odd, and limits are recomputed taking l is equal to 0 to l is equal to n by 4 minus 1 as the lower and upper limit, which is same for both the summations. Once again, we can observe that the above equation g of k reduces this time, and in terms of the new index we have 4l and 4l plus 2. We have the subscript which is wn by 2, which can actually be reduced by using the property of the twiddle factor. It can be expressed as wn by 4 raised to lk and wn by 4 raised to lk. So this gives you the further level of decimation, wherein g of k is ultimately expressed as 2n by 4 point DFTs, which may be named as pk and rk. And similarly, the other term h of k can also be represented using help of 2n by 4 point DFTs called as q of k and s of k. So this way the procedure will carry on until the very last stage. In the final stage of decimation, we should observe that we should not have any of the blocks n by 2, n by 4. Each block should be replaced with what is called as the butterfly structure. Now here is a simple 2-point butterfly structure. This will show you the final replacement, wherein the 2-point DFT becomes a structure as shown here. Hence, we can replace all the blocks and we end up with the signal flow graph for the DIT method. So after the substitution of each stage with the respective butterflies and using the appropriate formula for simplifying the twiddle factors, we get the final signal flow graph for n is equal to 8. Some quick observations about this structure. First thing, this structure has 3 stages. For value n is equal to 8, we have 3 stages in DIT. The input index is not sequential. In fact, this is called as bit reversed indexing. The output happens to be in order, so we can say it is sequential. The size of the butterfly in this case is increasing. The twiddle factor is multiplied before we perform the operation of addition and subtraction. So for each butterfly, the basic operations remain the same, the structure also remains the same. So at the top we can say we are performing additions of the inputs. The first input is x of 0, the second input is x of 4, which is scaled by the twiddle factor. So here we add those two numbers, and since we have a scaling with -1, it is treated to be a subtraction operation. So the top node is an addition of the two inputs and the bottom node is the subtraction of the two inputs. This concept remains same irrespective of which place the butterfly is. All the butterflies are same. So practically the lower arm of the butterfly is where we do scaling and where we multiply with -1. So this arrangement is called as decimation in time. The number of twiddle factors that we need here are 4. So for value n is equal to 8, we require half the number of twiddle factors, which is ranging from w8 to the power of 0 up to w8 to the power of 3. Now, few more observations that we can make. From the above signal flow graph, we observe that there are 3 stages and each stage requires 4 multiplications. Multiplying by twiddle factor is treated to be one multiplication. So there are 4, 4, 4 in each stage, or generally speaking, we can say it is n by 2 multiplications in each stage. The number of stages is said to be log n to the base 2. Therefore, the total number of complex multiplications is equal to number of multiplications per stage into the number of stages. Each stage has n by 2 multiplication. Number of stages is log n to the base 2. Coming to the number of complex additions, each stage will have n additions. The operation of addition and subtraction is treated to be addition. So if we count here 1, 2, 3, 4, 5, 6, 7, 8, we have a total of 8 additions. It is same for all the stages. Therefore, there are n additions in each stage and the number of stages is equal to log n to the base 2. Hence, we arrive at the formula for computing the number of complex additions as n times log n to the base 2, and the number of multiplications is half that number, that is n by 2 times log n to the base 2. The formula for the number of stages is log n to the base 2. Thank you all.